Hello and welcome to our second lecture of information theory and application. Today we start really getting into the matter of the subject, and we are going to introduce some fundamental quantities: entropy and mutual information, and another quantity called divergence, which is even more general, which will serve to state the main results of information theory. Before entering uh, the treatment of these information theoretic quantities, I want to stress the fact that it is very important in this course to have a decent background in elementary probability, random variables, and a little bit of random processes. In particular, continuous and discrete random variables, their PDF, probability density functions, PMF, probability mass functions, and, concepts about probability spaces, events, joint events, union of events, and conditional probability. So if you have attended my course of probability and random processes for electrical engineers last semester, you will not have any problem here. If you're coming from another direction, another program, or another school which is not TU Berlin, I hope you have the right background. Otherwise, I advise you to take a look at this background by yourself. This is a homework, self-study, and is necessary because otherwise you will get very easily lost in the notation and in results that we're going to use routinely, and I cannot, re-explain the whole probability theory in this course because this would be out of place. So here I have indicated some sources that you can use to study this material, to review this material. Chapter 1 of this book by Robert Gallagher, who's, by the way, one of the most important information theorists of all times. After Shannon, he was a professor at MIT. Now he's still alive, but retired, and is still a great, great, great scientist. And I wrote books in information theory, and I wrote also books on stochastic processes and probabilities and networking, a lot of things in communication, networks, electrical engineering. And in particular, there is a nice book on stochastic processes that have a chapter 1, which essentially reviews all these elementary materials, which is all what you need here. Otherwise, other chapters, other books, these other two references are also good. In particular, the book of Grimmett and Stiltzecker is extremely exhaustive, extremely deep, not particularly easy to read. So it depends, on which level you need to review this material. Anyway, those are proposed sources. If you have other, I don't know, Wikipedia, online courses, you can choose whatever you want, as long as you have the right background. And this is not very complicated. This is very elementary. So any decent course in probability will allow you to understand. So a little bit about notations and some introduction. So let's first talk about the concept of random variable. What is a random variable? Well, the mathematical definition, the formal definition is complicated. You can review it. But to me, random variable as we use it here can be thought intuitively as a sort of random number generator. You push a button and the random variable spits you a random answer. And the random answer is a symbol in a certain alphabet. For example, I use calligraphic letters. So here you see calligraphic capital letters like X calligraphic to denote the set or alphabet of symbols that the random variable can generate. I use analogous non-calligraphic letters like this capital X to denote the random variable itself. And to make an example, suppose that we have an alphabet that contains the numbers 0, 1, 2, 3, 4, 5. Then a particular value of the random variable, so a particular symbol that the random variable can generate is any of symbols. So in this case, it will be one of these 6 numbers. I call it A belonging to X. And then basically you can say the random variable responds to a sort of random event, like flipping a coin, and voila, gives you one of the symbols with a certain probability. Then you flip the coin again, and it gives you another symbol with a certain probability. And so we collect the probability with which X generates values in its alphabet, and the collection of these probabilities is called the probability mass function, PMF, of the random variable, and it is denoted as this symbol here, P sub X of an argument. P sub X. Now the argument, instead of this dot here, in this dot, can take any value inside the alphabet. So we are going to have, for example, P sub X of 0 will be the probability with which my random variable takes on the value 0. And P sub X of 1 will be the probability with which my random variable takes on the value 1, etc., etc. So the collection of all these values forms, in fact, a function that maps the alphabet to the interval 0, 1, because each of these probabilities, being probabilities, must be a number from 0 to 1. So a note on notation is that the symbol P sub X of the argument says that P sub X is the PMF of the random variable X. X here is not an argument of the function, it's just a reminder. It's just to say that P sub X is the PMF of X. If I had another random variable called Z, I would call its PMF P sub Z. Okay? The argument is here. The argument, you read it here. And for every A in X, this P sub X of A is a number from 0 to 1. And these numbers are probabilities, so they have a property, some properties. The first property is that, well, they are numbers from 0 to 1. The second property is that if I sum over all values in the alphabet, so I sum over A, P sub X of A, I find 1. So alternatively, we may consider a PMF as a vector. We have a finite size alphabet. I use this symbol to denote the cardinality of a set. The cardinality is the number of elements in the set. So if I collect all these probability values into a vector with a cardinality of X components, so the vector P, I use bold letters to indicate vectors, and therefore this will be the probability vector collecting P1, P2, P3, those are all the values. So P sub I is the value of the PMF evaluated at the ith symbol in the alphabet. So it's P sub I is equal to P sub X of A sub I. A sub I is the ith symbol according to some ordering. And then this forms a vector. And this vector has the following properties. The property number 1, its components are non-negative, they're all numbers from 0 to 1. The second property is that summing over all the alphabet, the sum is 1. So to make a silly example, take X as the set of 26 characters of the English language, enumerated in lexicographic order. So the first symbol is A, the second symbol is B, the third symbol is C, and so on. Then suppose that P sub X of Q is 0.001. It means that with this probability, a random variable X that takes values in this alphabet generates the letter Q. Okay? And Q is the 17th letter of the alphabet, so P sub 17, so the 17th element of the corresponding probability vector is equal to 0.001. Okay? So I hope that this example clarified the notation. Now, another important concept that we will use all the time is the concept of expectation. So what is the expectation? Well, first of all, let's notice that given a function g that maps the alphabet x into the real line, so it takes real values. Basically, this function associates to every letter of the alphabet a real number, g of a. Okay. So if I evaluate this function at the random variable, well, that's a function of a random variable is a random variable itself. So g of x, since x is random, then the value g of x is a random value. Okay. And I can define the expected value of this function of random variable, and I use this symbol, e brackets with something inside. The g goes here inside. So e means expectation of g of x. And this is a definition, is the sum over all the letters in the alphabet of the value of the function times the probability of this value. Okay? So if you think for a second, you recognize immediately the usual, probably you have seen the mean value of a distribution. So homework, review the properties of the expectation operator. In particular, an important property is that the expectation operator is a linear operator. A linear operator means that if we have a collection of random variables, x1, x2, xn, define a common probability space for which they exist in the same probability space, so they're well defined, and then they take values in their own alphabets, and we have a collection of functions that map these random variables into real numbers, and then we take a linear combination. So we take a fixed set of coefficients, non-random, and we write here this linear combination, which is simply the sum over I of alpha I gi of xi. Well, that's a linear combination of these functional random variables. It turns out that the expectation of the linear combination is equal to the linear combination of the expectation. So in other words, the expectation operator commute with the linear combination. It's a linear operator. Okay. So a few more concepts in probability that we will use later on. Joint probability and statistical independence. So again, homework, review this concept if you're not familiar with. So now we consider more random variables defined on a common probability space. For example, let's start with two. We consider two random variables, x and y, each one taking on values on their own alphabet. And then the distribution of the pair x and y is called the joint probability mass function. So that's just the extension of the concept seen before. Now we have a new alphabet, which is the Cartesian product of the two alphabets. This contains all possible pairs A and B, where A is in X and B is in Y. That's the definition of Cartesian product. And now we can think of the pair X and Y as a single random variable, but now it takes values on this Cartesian product alphabet. So every determination of X, Y is some pair A and B, where the first component A is in X, the second component B is in Y. And we are interested in the probability of the joint event that simultaneously X takes on values A, Y takes on values B. This comma in between is read in probability end. It's really like the logical end. So it's simultaneously the end condition, the condition X equal to A and Y equal to B are simultaneously true. Okay? And we say that the two random variables are statistically independent if the joint probability, so the probability of the joint event, factors into the product of the individual probabilities. Huh? So if the joint probability is equal to the product of the individual, called also marginal probabilities, and this happens for every A and B, of course, not just a special case, then we say that the X and Y are statistically independent. Written in terms of probability mass function, this means that the joint probability mass function, P sub X comma Y with argument A comma B, is equal to the product of P sub X of A times P sub Y of B, and this must be true for every A and B in X Cartesian product Y. Okay? Good. Oopsie. Okay. So now that we have defined the concept of statistical independence, we can also introduce the concept of IID sequences. So, first of all, what is a random sequence? A random sequence is simply a sequence of random variables indexed by a discrete index that takes integer values 1, 2, 3, 4, 5 that conventionally we can call time. Okay, so sometimes they are called like discrete time random processes, but you know, it could be space, it could be whatever. We identified with time because normally when we think about an information source, we think of something that spits out characters from an alphabet one at a time, tak, 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 at a certain rate. So we use the notation X sub I in curly brackets to indicate a generic random sequence where the generic element is the random variable X sub I, without specifying the beginning and the end. It may be infinite, say from 1 to plus infinity, it may be doubly infinite from minus infinity to plus infinity. When I write this, it means that either it is clear from the context or it is irrelevant. Okay? If we like to specify the beginning and the end of a sequence, I'm going to use this notation. X with one subscript and one superscript, and these are not exponents or whatever. This means from to. So it's xn, x plus 1, until x m, with the convention, of course, that if the upper index is less than the lower index, the sequence is empty. So there are no elements. So basically, it's like a constant sequence that contains no elements. For brevity, when the initial index is 1, we just specify the upper index. So x to the n is not x raised to the power n, please. It's not in this context. It means the sequence from 1 to n of the random variables x sub I, x1, x2, x3. So it is when a sequence, a random sequence, has a finite dimension, like in this case n is finite, we call it a random vector. Okay, so that's a random vector, x1, x2, xn, n-dimensional random vector. So unless said otherwise, when we use the same letter x sub I to indicate these random variables, it is almost always, let's say, assumed that the alphabet in which these random variables take on values is the same. So in other words, a realization of these random variables is an element in the Cartesian product x times x times x. Those are all the vectors of length n with elements in the alphabet x. How many are they? Well, it's cardinality of x to the n, right? And and that's it. And sometimes we, not sometimes, always, when the n-fold Cartesian product of an alphabet by itself is indicated as x alphabet to the n. Okay, this means the n-fold Cartesian product of x by itself n times. Okay, so an n sequence x n takes values in the Cartesian product alphabet x to the n, which is simply all the sequences with elements in x. And of course, we can generalize the concept seen before for two random variables to the case of n random variables and define a joint n-dimensional PMF, which will be P sub xn of A. A is a vector of n components whose elements, every element here, belongs to the alphabet x. Okay? And this is the probability of the joint event x1 equal to a1 and x2 equal to a2, blah, 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 till xn equal to an. Okay? Now, the sequence, the random sequence, is called IID, which means independent and identically distributed with a certain common marginal probability mass function px, if for any set of indices and any set of values, the joint probability factors in the product of the individual probabilities, and in particular this means that the joint probability mass functions of these values of these random variables factors in the product of the individual probability mass functions that happen to be always the same function, p sub x, evaluated, of course, at different arguments. So this is the concept of IID sequences that we will play an important role later on for almost all this course. Another important concept is the concept of conditional probability. So I will not tell you now all the story about events, probability spaces. This is something that you should know. Let me just remind that if we have two events in a common probability space with a probability measure P. Oh, by the way, I didn't say before, sorry, I say it now. I use this symbol with this strange P to indicate the general probability measure underlying the probability space. And so any probability can always be written as P of some event. Events can be, for example, x equal to a. That's an event. Or x less or equal than 3. This is another event. Okay? It depends on the probability space. So we use this generic symbol, but when we write these probabilities in terms of probability mass function, then we use the probability mass function symbol that we have introduced before. Okay? So in general, we say that the conditional probability of an event B given another event A, when the probability of the conditioning event is greater than 0, so we say that the conditioning event is not null, is given by this ratio, is the probability of A and B, which is the joint probability, divided by the probability of the conditioning event. When the conditioning event is null, so the probability is 0, then the conditional probability is not defined. It doesn't exist. So correspondingly, we can define a conditional probability mass function of y given x as this function, P of y given x, given is bar, and comma is n. So n comma given bar. This is, the notation is important. If you confuse them, then you make mistakes. Anyway, I was saying the conditional probability mass function of y given x, calculated at two values b and a, is the probability of the event y given b given the event y given a, which is, of course, as using this definition in here, the joint probability mass function of x and y calculated at a comma b divided by the conditioning probability mass function px of a. So from here we have the so-called telescopic property of probability, that when we have probability of 3 or more, I say it for 3 just to make the case, but it can generalize to any set of events. So we have here this event x equal to a, then we have here and this event and this event, right? Taken in any order, it doesn't matter, because and is a logical condition, so it doesn't matter if it is the first event and the second, or the second and the first is the same. And means intersection of those events. They have to happen all simultaneously. But this probability can always be developed in terms of products, or just take one event as first. In this case, we take the yellow event. So we write it is a probability, oopsie, making a mess, probability of a equal to x equal to a. Then the second event is probability of y equal to b given x equal to a. So the second given the first. Then we go to the third times the probability of the third given whatever comes before. Okay, this is called the telescopic property of probability. We can develop any joint probability into the product of conditional probabilities, where every time you take here, at every term, you take here the new event and condition of all the old ones, the ones have been already included. Okay. So written in terms of probability mass functions, you have this writing here. Okay, this one. And of course, if I generalize this to n random variables, but I have writing, concisely with the notation we have introduced, we have this product form. This is the general telescopic property of probability, which will be used later to derive something called chain rules for entropy and mutual information, which are very useful expansions to somehow take complicated terms and break them down into simpler terms. So, last remark about notation. So far, for the sake of clarity, I have clearly distinguished the letters or symbols in an alphabet using A, B, and C, and the random variables X, Y, and Z, etc. So since later on we are going to handle expressions with many different random variables, each one has its own alphabet, each one takes its own values, then it becomes very messy to make this distinction. So we are going to use capital letters X, Y, Z for the random variables, the corresponding capital calligraphic letters for their alphabet, and the small corresponding letters to indicate the particular symbols. So for example, we can say an n sequence xn with this component x1, xn, those are random variables, takes values in the n-fold Cartesian product alphabet calligraphic X to the n, and a possible outcome is simply a vector of specific values using the small letters. It's easier to use the same letter. It's more confusing to say because I'm going to have X, X, X. I cannot always repeat capital X, small x, calligraphic X, etc. But when you see the formulas, it's easier to identify random variables, their alphabets, and the symbols they take on values in with the same letters because it's easier to recognize it. Okay, so at this point, this mini lecture stops here, and the next mini lecture starts using this notation to introduce important information theoretic quantities that will be part of this first, say, chapter 1.